So today I will be going to speak on on plotting 100, 110, 111 pole figures in the cube orientation, which is considered to be the simplest orientation. That is because if we just look at any surface, for example a rolled surface, for example a given specimen, if we just talk of that, so we have the two types of coordinate systems. The first is the crystal coordinate system and the other one being the sample coordinate system. So if we look at the crystal coordinate system, we have in the case of cubic crystals, we have 100, 010 and 001, and also that the symmetries along the 100, 010 and 001 are basically the fourfold. But however, this is not the case in case of tetragonal, because 100, 010 and 001 don't have the equivalent symmetries because of the C by A ratio being greater than 1 in case of tetragonal and the other crystal systems. So today we are not bothered with those crystal systems. We'll be just talking of the cube orientation in the case of the crystals having the cubic crystal structure. So now let's consider the cube orientation. The cube orientation, why it is called the simplest orientation, is because the identity, if we just look at the relationship in between the crystal coordinate system, that is denoted by the symbol C suffix C, and the sample coordinate system, then they are basically related to each other by G matrix. What is this G matrix? Is basically the orientation matrix or the rotation matrix. Now the G matrix is basically equal to cos alpha 1, cos beta 1, cos gamma 1, cos alpha 2. So this is basically a 3 by 3 matrix, So if we just look at cos gamma 2, and then we look at cos alpha 3, cos beta 3, cos gamma 3, we basically have the alpha. What we basically do is the alpha 1 is basically the angle made by the rolling direction with the 110. Now what is this rolling direction and what is this 110? So to designate this, we'll take up we'll draw a cubic crystal over here. Okay, so we do is we draw a cubic crystal over here, where we take this, say, to be the x-axis, this to be the y-axis, z-axis. This is basically the rolling direction, this is the transverse direction, this is the normal direction. Okay, so also I wish to clear one thing in this context is, we are just talking of samples which have been rolled. We are not talking of any extruded sample or deep drawn sample. Okay, so what we do is, okay, so we have the x, y and the z axis, which are basically nothing but RD rolling direction, TD transverse direction, and ND, that is the normal direction. And so these are basically the specimen coordinate system. So so this is basically say, let's consider a bar of a rolled bar of steel, for example, a rolled bar of steel, where on the surface we have a lot of grains. Okay, so we can draw a lot of grains here on the surface and so on. So basically we will have the different the lattices. So now I consider only one of the lattices, wherein I have the specimen coordinate system, which is designated as RD, TD and ND. Now coming to the crystal coordinate system, so I already said the crystal coordinate system, for example, may be designated as 100, 010, and say this is 001. Okay, so this is all about the crystal and the sample coordinate system in this case, in this simple example. Now what is alpha 1? I already said that alpha 1 is the angle which is made by 100 with RD. Similarly, beta 1 is the angle which is made by the TD, transverse direction, with 100. Similarly, gamma 1 is the angle which is made by the normal direction with the with 100. So if you just mark this on this diagram, on this particular diagram, basically what we're going to get is, we're going to take this 100 and RD, the angle between that, to be alpha 1. Okay, the angle between that is the angle between TD and 100. So if we, okay, so this is basically the beta 1. Okay, this angle is beta 1. The gamma 1 is basically the angle which is made by the 001 with the ND. Okay, so here, here this comes out to be 90 degrees, but it may not be necessarily equal to 90 degrees depending on what orientation as well as what crystal system we are talking of. So this is gamma 1. Then we have alpha 2. Alpha 2 basically is the angle which is made by 100 with that is by RD, rolling direction, with the 010. So yeah, so this angle, so this particular angle is basically the alpha 2. So it becomes a bit clumsy now. Okay, so similarly we can one can also think of drawing the beta 2, gamma 2. So okay, well, let's okay, so for beta 2 is basically the angle which is made by the transverse direction with the 010. So the transverse direction with the 010 is basically yeah, so this angle, so this angle, so this is beta 2, and so on. So we can and then we have also the gamma 2. Gamma 2 is basically the angle made by ND, now normal direction, with the 010. So this is basically the gamma 2. Okay, then we have the alpha 3. Alpha 3 is basically nothing but the angle made by RD with 001. So RD with 001 means this angle is basically the alpha 3. Okay, so this 3. So we have the beta 3 again, so which is basically nothing but the angle made in between TD and 001. So TD and 001 is basically this one, this angle. This is again the beta 3, and finally the angle made in between the normal direction and the 001. So this is this angle is basically so that basically comes out to be equal to gamma 3. Okay, so this is so the diagram has become a bit clumsy, but this basically, this G is basically the orientation matrix, and or also called the rotation matrix. Now why this is significant is because it is basically one of the ways of representing any kind of texture. That is, when we talk of texture, we generally talk of representing texture by 4 methods. The first is representation of texture using the or in other words, determination of the orientation using the G method concept. This G is basically nothing but the orientation of the rotation matrix. Then secondly, we also talk of the angle axis representation, as well as thirdly we talk of the Rodrigues vector. Rodrigues vectors to represent orientation, and also fourthly and lastly we talk of the Euler angles. The Euler angles are basically nothing but the 3 different angles, phi 1, phi 2, which and one of the most commonly used conventions for determining the phi 1, phi and phi 2 is basically the Bungé's convention. So we are not going into that much of complexity. What we're going to take, or what we're going to think today, is how do we plot the 100, 110 and 111 pole figures in this orientation, this cube orientation. So to do that, so to do that, what we need to do is, first of all, we need to know about the stereographic projections. So I hope stereographic projections is clear to all the audience who might be listening to this. So stereographic projection is basically nothing but true angle projection. Okay, and there are various sources from which we may get references of the stereographic projections. So when we talk of any kind of texture, say 001, 100, the immediate thing that must strike in our mind is the 001 refers to the ND, normal direction, and this is HKL. Basically this is the way of representation of texture in general, and this UVW is basically the the rolling direction. So the RD. So this is the ND. HKL is the ND, which is basically the HKL, and then the UVW is basically nothing but the RD, or the rolling direction. Okay, such that the UVW must lie on HKL. Okay, so if we think that UVW must lie on HKL, the immediate thing that comes to our mind is the Weiss's zone law, which basically says nothing but that that the HU plus KB plus LW is equal to 0. Okay, so this thing we have to keep in mind. Okay, now when we talk of when we draw the stereogram for the 001 in cubic, we basically have the 001 at the center. We draw a straight, so we can just plot this. It will take only a little bit of time. Okay, so this is 0 1 0, 0 bar 1 0, bar 1 0 0, this is 1 0 0, this is 1 bar 0 0, oh sorry 1 0, this is 1 bar 1 0, this is 1 1 0, bar 1 0. Okay, and the stereographic projection looks somewhat like this. Okay, so so what we need to do is basically through vectorial addition of this. So this is 0 1 1, and then this is 0 bar 1 1, and this is basically nothing but bar 1 0 1, and this is 1 0 1. So and then so this is basically the vectorial addition, that is 0 0 1 and 0 1 0. If we add up, we get this. Okay, so similarly if we also yeah, so if we basically so this is not 0, so this is 1 0 1 1, but this cannot be confirmed by only one vectorial addition. We also have to add this up so that we are able to arrive at this coordinate system, I mean at this coordinate. So basically if we just look at this again, so this is bar 1 1 0, so this is bar 1 1 1, this is basically 1 bar 1 1, this is bar 1 bar 1 1, this is 1 1 1. Okay, so if we just add this up, so this we get 0 2 2, and then we have to divide it by 2, so we get 0 1 1, and here also we get 0 1 1. So basically so this is 0 1 1, which is correct. Okay, through vectorial addition. So we can do this, repeat the same exercise for all the other for all the other planes. Okay, so that is for all the other planes. So basically we know that so these are basically nothing, these coordinates are basically nothing but the the various plane normals. These are not the poles, these are the plane normals. Okay, so I hope you know the difference between the plane normals and the poles. So this is basically the prerequisite before watching this video. So at the same time, so what you need to think of is a very simple orientation. This is 0 0 1, so this is the ND, and generally the convention is we take the topmost corner to be the RD, ruling direction, rightmost corner to be the TT, transverse direction. This is by convention, this is by general convention. And okay, and then what we need to do is we need to take this the center one is the ND. So ND is okay, ND is alright. This is 0 0 1. Okay, so now what we need to do is, so this is NT and this is RD. 1 0 0 is ND, I mean 1 0 0 is RD, and this is 0 0 1 is ND. So 0 0 1 is ND, it's fine. This may not be the situation in all the cases. For which case we have to rotate the stereogram, and then we have to do the required rotations in order to get the required ND. Okay, so the RD, so how do we get the RD? Because we find that this is bar 1 0 0. Although in cubic system the bar 1 0 0 and 1 0 0, due to the symmetry, they can be considered to be equivalent for constructing this 1 0 0 1 1 0 1 1 1 pole figures. But for the sake of learning, that is, suppose we are given the other systems, other crystal systems like tetragon. So there, what we can do, so there, this problem may not arise again, because bar 1 0 0 and 1 0 0 again through symmetry they are equivalent in tetragonal. But if it is 0 0 1 and 0 1 0, they are never equivalent. So in tetragonal. Okay. So what we need to do is we need to rotate this 1 0 0 clockwise, or we can also do it anti-clockwise, whatever we wish, by about 180 degrees about 0 0 1, so that ultimately we are able to have 1 0 0 at the top. So I will show that on the next page itself. So you can have no this, suppose this is 0 0 1, this is 1 0 0, this is bar 1 0 0, this we can join. Okay, so everything, every pole will get rotated by every plane normal, so every plane normal will get rotated by 180 degrees. Okay, so if you look at here, if you look at this will go, so for example this 0 1 bar 1 0 will go somewhere here, this will go here, this will come here. So also all normals will rotate by 180 degrees. So what we do is, if you just write here, okay, so we can do one thing, we can drawing the histogram there. Okay, so you can also do the vectorization and all. So yeah, so this basically shifted here. Okay, so again, so what we can do is, this is again 0 1 1, this is very simple. So this is 1 0 1, this is bar 1 0 1, this is bar 1 1, this is bar 1 1 1, this is 1 1 1, and this is basically nothing but bar 1 1 1. Sorry, I'm sorry. So bar 1 1 1. So sorry, bar 1 bar 1 1. Okay, bar 1 bar 1 1. So what we can do now is, we have to have, so we already have our orientation. This is basically nothing but 0 0 1 1 0 0 orientation. Okay, because 1 0 0 lies parallel to the RD, and 0 0 1 lies parallel to the ND. Okay, now the question that arises is, how do we construct the 1 0 0, 1 1 0 and 1 1 1 pole figures? Okay, so to do that, the next step would be to do that. This 1 0 0 pole figure, if we just construct, so 1 0 0 pole figure is nothing but, where are my 1 0 0 poles which are lying. Okay, lying. So if we just draw a simple pole figure space, and we have this, so we have the 0 1 0 here. So this is basically one of the 1 0 0 pole figures, because because in cubic, the basically, if we write this 1 0 0 pole figure, 1 0 0 also not only implies 1 0 0, it also implies 0 1 0 and 0 0 1. Okay, however, for tetragonal 1 0 0 pole figure does not imply the 0 0 1, because 0 0 1 is different than 1 0 0 and 0 1 0. They are not equivalent. But obviously in cubic, due to the symmetry, 1 0 0 is equivalent to 1 0 0. This can be bar 1 0 0, 0 bar 1 0, 0 1 0, 0 0 1, 0 0 bar 1, and so on. So what we can do is, we can just have so as we already said, I think in the beginning of my talk, that 1 0 0 basically in cubic has a fourfold symmetry, or fourfold axis of rotation. So basically in crystallography, we represent the fourfold axis of symmetry with the help of a square. Okay, so if we just look at this 0 0 1 1 0 0 pole figure, we have in the center, at the center we have a square. There's 0 0 1. We have this there are two centers, two squares we can draw here. We can also draw two squares here. Okay, so this basically gives us the 1 0 0 pole figure. Similarly, 1 1 0 pole figure, if we want to draw, so 1 1 0 in cubic will have nothing but so they will be having nothing but the twofold symmetry. Okay, but there is a twofold symmetry. So as they have a twofold symmetry in crystallography, the 1 1 0 pole figures have to be represented with the help of an ellipse. Okay, so basically again, if we draw the pole figure space to represent the 110 pole figure now, so what we need to do is obviously we can divide it into 4 quadrants. So again, we divide this into again 4 quadrants. So the 110 pole figure here is basically represented here by this. Yes, 110 family there. So 110 family we already know, right? So that so 101, 110, 011, again 1 bar 1 10, 1 bar 10, and then 10 bar 1, 01 bar 1. So all so we have the 12 such planes there, excepting the parallel planes. If we consider the parallel planes, we have 24. But still, so what we need to do is here, if we just look at the diagram, the 110 pole figure can be drawn somewhat like this. Okay, so yeah, perfect. So that's done. Yeah, so so this is basically the 110 pole figure. And why it is an ellipse, so I am not speaking of the crystallography here, but due to possessing the two-fold symmetry in cubic, the 110 planes, the plane which possess the two-fold symmetry there in cubic, so the general convention to represent the two-fold symmetry is basically in the form of an ellipse. Now what comes is the 111 pole figure. Now I'll be drawing this in the next page. The 111 pole figure, again, we have the threefold symmetry which is present in the 111 planes, okay, in cubic. So we represent the 111 poles in the pole figure space with the help of an equilateral triangle in crystallography. Again, so this is 111 pole figure. How to do that is very simple. Again, just follow the same procedure. So this for example, here, and here are my 111 poles. So what we can do is, and nowhere else we can see the 111. So what we can do is, again, if we draw 4 quadrants here in the pole figure space, so please forgive because this is actually lying in the center. So we can basically have the 4 triangles here. So these are basically representative of the 111 pole figure. Hope you enjoyed the video. Any comments that you have, please post. Thank you.